In this video, we're going to review finding domain and range, both graphically and algebraically. So let's start with a problem in which we're asked to find the domain and a range based on the graph of a function. So here's my function. We're not given an equation here, just the graph, and we want to find the domain and range based on this picture. So let's start by thinking about the domain. So first of all, let's just mention what the domain is. So the domain of a function is a set of all x values for which a function is defined. So when I'm trying to determine the domain graphically, what I'm looking at is I'm looking for the x values where the function exists. Now remember, my x values are horizontal here, right? My x values are on this horizontal axis. So let's start by thinking about the left side of the graph and what's happening over there. So on the left side of the graph, if I just follow the function here, the graph is just continuing forever in this direction. That's what this arrow signifies. So that means that my x values are going to go all the way to negative infinity, right? The x values for which this function exists keep going and going and going to the left forever. So I'm just going to mark that on my horizontal axis here. Okay, and then let's think about what's happening on the right end of the graph. So if I look at the right end of the graph, and once again I'm thinking about x values here, right? So I'm thinking about what's happening in the horizontal direction. I see that my function ends at a specific point, right? There's this open dot where the function ends, and that's at an x value of 3. And beyond that, to the right of that, the function doesn't exist for any x values to the right of 3. Now, but in between negative infinity and 3, all the x values are included, right? I don't see any holes or jumps or any other sort of discontinuities that I would need to take into account. So then, it looks like my domain is going to be the interval from negative infinity to 3. Okay, and I'm putting an open parentheses on 3 here to signify that the 3 itself is not actually included in the domain. And once again, what I'm saying here is I'm saying that this function exists for all x values between negative infinity to 3. Now let's talk about range. So the range of a function is a set of all output values, or y values. So we're going to think about this in a very similar way. We're just going to be looking at the y values instead of the x values. So I want to think about the y values for which this function exists. So let's start by thinking about a lower bound, or the bottom of the graph. So I'm looking at y values, which are vertical here, right, along my vertical axis. And the lowest y value I see here is at negative 2. Right, and that point it is included on the graph. The y value of negative 2 is included. So that's my bottom bound. Let's think about if there's a top bound. Well, remember that on the left-hand side of my graph here, I have this arm of the function that's just continuing to go up and up and up forever, right? This just keeps going up forever and ever. So then it doesn't look like there's going to be an upper bound on our y values, right? Our y values are just going to continue to positive infinity at the top of the graph. Now we also want to just check our in-between values here and make sure that there's no holes or anything that I need to take into account. So I do have this hole here at the point 3, 3, right? So at a y value of 3, I have this hole here, but if I look on the other side of the graph over here, I see that a y value of 3 is included on this side of the graph. So then I would want to include a y value of 3 in my range. So then it looks like my range overall is going to go from negative 2, that's my lower bound, and I'm going to include it with a bracket since it is included on the graph, a y value of negative 2, and then all the way up to positive infinity. Okay, so once again, the range, that is all the y values that I see represented on my graph here. So that's how to think about domain and range graphically, but let's look at a few examples where we need to determine domain and range algebraically. Here's my first example. Determine domain and range for f of x equals x squared plus 7x minus 6. So domain means the same thing in this context, in this algebraic context, but the way I think about it might be slightly different. So once again, the domain of a function is the set of all input values, or x values, for which a function is defined. So one way to think about that is the set of all x values that I am allowed to plug into this function, or the set of all x values that when I plug them into this function, I get a real output. So when you're thinking about this, it can be helpful just to know a little bit about the different types of functions you may encounter. So here I have this function x squared plus 7x minus 6, and perhaps you remember that this is what's called a quadratic equation, and its graph looks like a parabola. So knowing that can help us a little bit when we're thinking about the domain of the function. So in this case, I just want to think about if there are any limitations on the x values that I could plug in here. But in this case, there's not. Okay, so any x value that I plug into this function, I'm going to get a real output. So let's think about plugging in some negative x values. Maybe something like negative 20 or negative 2 or negative 5. Any of those negative x values, if I plug in here, you can picture this in your head, and I work through my computations, I'm going to get out some real value for the function. I can also plug in 0, right? If I plugged in 0, I get 0 squared plus 7x minus 6, so I'd get negative 6. So that's real. That's something I could see on a graph. I could plug in positive x values. There's no x values that I can't plug in here and get out something that makes sense. So what that tells me then is my domain is what we call all real numbers, or we may write that as negative infinity to infinity. And that makes sense based on what we know about the shape of this function, right? We just said this was a parabola, right? So I don't know exactly what it looks like, but in general, it's going to have this sort of shape, so it continues to the left and to the right, right? So all x values are going to be included on this graph. But let's talk a little bit about range in this case. And range for this function is perhaps a little complicated. But once again, it's kind of helpful to know what sort of shape we're dealing with here. So we've said we're dealing with a parabola, and specifically because this leading term, this x squared, is positive, we're dealing with a parabola that opens up. Okay, so then what should we expect for our range? Remember, the range is the y values, or the output values. So we should expect some lower bound on our range. And then upper bound would just be infinity, right? These ends are going to extend upward forever, but there should be some lower bound on our range. So there are several ways we could go about this. You may or may not recall the fact that there's a special formula to be able to find the vertex of a parabola. And the vertex of a parabola happens at the x value of negative b over 2a. Where the b and the a refer to the coefficients of my terms here in the same way they would for the quadratic formula. So in my case, b is 7 and a is 1. So I get that the vertex is at an x value of negative 3.5. And then I can, of course, plug that x value into my function to find the associated y value. And I'll spare you the details here, but if I plug in negative 3.5 to this function and evaluate, that I'm going to get negative 18.5 18.25. So then this point down here at the bottom of my parabola is the point -3.5, -18.25. So that vertex is a minimum value for my function in this case. So then once we know that, we can write down the range. The lower bound of the range is just going to be this -18.25, which I want to include, and then we're going to extend upward to y values on up to infinity. You could verify this information with a graph as well. If you had access to a graphing calculator, that'd be a perfectly good way to think about the domain and range for this problem. And indeed, here is a graph of our function, and it seems to agree with what we said. Domain of all reals, all x values, and range from -18.25 on up to infinity. Now let's think about the domain and range algebraically for functions that are a little more complicated. So here I want to find the domain and range for a, f of x equals the square root of x, and b, f of x equals the square root of 2 minus x. So these kind of functions, root functions or radical functions, are really important to know how to find the domain of. So let's talk about how we would do this. So these are square roots. So let's think about domain first. And remember, when we're thinking about domain, we're thinking about the x values that we're allowed to plug into the function, the x values that will give us a real output. And square root functions are a little special, right? There's some limitations on what I can take the square root of. So hopefully you know that if you try to take the square root of a negative number, you're going to get an imaginary result, right? So for example, the square root of -4 is what we call an imaginary number. It's not a number that I can see on a graph. But I can take the square root of positive numbers, and I can also take the square root of 0, right? The square root of 0 is 0. So then to get a real output from my square root function here, I need whatever is underneath the square root to be either 0 or to be positive, right? I just don't want it to be negative. So then using that, let's start with part A here. So if I want what's underneath the root, which in this case is just x, to be either 0 or positive, the way I could write that is x is greater than or equal to 0. And that's going to be my domain in this case. Just simply this, x's that are greater than or equal to 0. But I can write that in interval notation if I want, as bracket 0 to infinity. Right, so 0's in my domain, I can take the square root of 0. 1's in my domain, 2 is in my domain, and so on. But numbers like -4, -16 are not in my domain because they're going to give me an imaginary output. Okay, so I should probably write that this is the domain. But now let's think about the range. Once again, knowing a little bit about how the square root behaves will help us think about how to find the range in this case. So remember that the range is the set of all output values of the function. So in this case, I can think about what are the possible outputs that the square root will give me. So let's think about positive, negative, 0. That's often a good place to start. So if I take the square root of a number, can I get a positive result? Well, definitely, right? The square root of 4 is positive 2. The square root of 16 is positive 4, right? So it's definitely possible for me to get positive outputs from a square root function. What about 0? Can I get 0 as an output? Well, the square root of 0 is 0, so yeah, it looks like I can get 0 as an output. What about negative numbers? Is there anything you can take the square root of and get a negative output? No. There's no x's that I can stick in here that are going to give me a negative output for my function. So I don't want to include any negative numbers in my range then. But it looks like 0 is fine, and it looks like all positive numbers are fine. I can I can picture getting any positive output out of this function if I plug in the right x value. So then my range in this case is also going to be 0 to infinity. And let me just quickly show you a graph of the square root function to verify this. So this is the graph of y equals square root of x. This is a really good function to be familiar with the graph of. So actually all square root functions have this general shape, though they could be shifted up or down or flipped, but they all have this basic shape. So we see then that the domain, which is the x values, is actually starting at 0 here and then continuing to infinity, and the range as well, right? My y values start at 0 and then go on up to infinity. So it looks like we were correct on this domain and range. So then let's move on to part B. Part B is also a square root function, but it's just a tad more complicated, right? Instead of just the square root of x, I have the square root of 2 minus x. But our logic is going to be exactly the same. All right, let's start with the domain. And remember what we said about the domain is that we needed what was inside the square root to be either 0 or positive, right? Because we cannot take the square root of a negative number. So what I'm going to do is I'm just going to take this entire expression that's under the root, which is 2 minus x, and say that I need that to be greater than or equal to 0. And then in this case, I just have one small extra step. I just need to solve this inequality for x. So I can write that 2 is greater than or equal to x, which is equivalent to x is less than or equal to 2. So that's my domain. X is less than or equal to 2. So in interval notation, that would be negative infinity to 2 with a bracket. So basically, when you're finding the domain of these square roots, you're just going to take what's underneath the square root and set it greater than or equal to 0 and then solve for x. That's the basic algorithm you can follow. Now what about the range? The range is actually going to be the same as it was for part A, and for the same reason. Here I have just a square root, so the only outputs I can get out of this are either 0 or a positive number. Right, once again, I can't get a negative output from a square root. So then my range is just going to be from 0 to infinity. Once again, let's verify this on a graph really quick. So here's my graph of the square root of 2 minus x. We said the domain was negative infinity to 2, and that looks like it agrees, right? The domain are my x values here. I am extending all the way to the left, but I've got this right bound of 2. And then my range from 0 to infinity. Right? Y values start at 0 and then extend upward to infinity. Okay, so this is always how you're going to find the domain of a square root. And actually, I should mention that this process is going to be true for any even root. So for example, if I had had the fourth root of 2 minus x, if that was my function, I would have approached finding the domain in the same way. Right? Because just like I can't take the square root of a negative number, I can't take the fourth root or the sixth root or the eighth root of a negative number as well. So this process is going to apply to any even root. But let me actually add a part C onto here, and let's look at a different function. Let's say the cubed root of 5x minus 1. Now notice how this is different from parts A and B. Parts A and B were square roots, and part C is a cubed root. So that's going to affect how we think about the domain and the range. So what's different about a cubed root as compared to a square root? Well, a square root, as we've said many times now, I cannot take the square root of a negative number. The square root of a negative number is imaginary. But I can take the cubed root of a negative number, right? For example, the cubed root of negative 8 is negative 2. Right? So the cubed root of a negative is real. So then what does that mean for the domain? Well, I can take the cubed root of a negative number, any negative number, and I can take the cubed root of 0, and I can take the cubed root of any positive number. So basically, there's nothing that I can stick under that cubed root that isn't going to give me a real output. So what that means then is my domain is going to be all real numbers, or negative infinity to infinity for this cubed root. Same logic for the range. Let's now think about the outputs. So for a cubed root, like this one here, I'm going to be able to get negative outputs. And I could get any negative number out of this if I put in the right x value. And I can get outputs of 0, and I can get positive outputs, right? Any positive output if I put in the right x value. So basically, there's no limitations on the output that I can get from this function. So then my range is also going to be negative infinity to infinity. And if we quickly look at a graph of this cubed root function, we see that it agrees with what we found. This continues on both ends here. Right, so all x values are included, and as this extends in either direction, all y values are also going to be included. In this last example, we're going to think about finding the domain of what we call rational functions. So these are functions that have that look like fractions, like this. We call these rational functions, and these have special domains. So once again, domains, I'm thinking about the x values or the input values. What input values can I put in here and get out something that makes sense? Now, the limitation that I have with a rational function is the fact that I don't want to get a 0 in the denominator of a fraction. Right? A 0 in the denominator of a fraction causes issues. So I don't want that. So basically, in general, the domain of a rational function are all real numbers except any numbers that are going to make my denominator equal to 0. So let's start with part A. In part A, I have f of x equals x plus 1 over x minus 2. And so I know that my domain is going to be all real numbers, so I can plug in any number for x here except any x's that are going to make the denominator 0. So the denominator equaling 0 is going to happen if x minus 2 equals 0, which happens when x equals 2. So this is what we might call an exception to our domain. So my domain then is all real numbers except for x equals 2. But let's write that in a little bit of a nicer way. Let's use interval notation. So basically, I want to go from negative infinity to infinity, but skip over 2. So I'm going to go from negative infinity to 2, union 2 to infinity. And that's the domain of this rational function. So using the same logic then, let's look at part B. This is also a rational function, but it's just a little bit more complicated. I have 2x over x squared minus 2x minus 3. So once again, my domain is going to be all real numbers except any x values that are going to make my denominator equal to 0. So basically, I want to see if x squared minus 2x minus 3 equals 0 has any solutions. Okay, so to see if this has any solutions, we can try to factor it. So let's see if this guy factors. So I can actually factor this into x minus 3 times x plus 1. So then I get solutions of x equals 3 and x equals negative 1. So then my domain is all real numbers, and I can write it like this also, except negative 1 and 3. But let's also practice writing that in interval notation. I basically need to include every number except negative 1 and 3. So I need to go from negative infinity to negative 1, union -1 to 3 union 3 to infinity.